As we jump into Module 7, we're taking a look at Chapter 5 in our textbook, covering the area of analysis and design of beams for bending. So within this module, we're going to take a look at the analysis of the design of beams, which are structural members supporting loads applied at various points. We'll take a look at different applications, point loads, distributed loads, along the member. So now in most cases, the loads are perpendicular to the axis of the beam. Now, the transverse loading causes only bending and shear in the beam. So that's something right there. The transverse loading causes only bending and shear in the beam. When the loads are not at right angles to the beam, however, they also produce axial forces in the beam. So understanding where those forces are and are they at right angle to the beam or not is going to become important. So within this module, what are we going to do? We're going to draw out our shear and bending moment diagrams using static equilibrium applied to sections. We're going to describe the relationships between your applied loads, shear, and bending moments throughout the beam. We're going to use sections modulus to design beams. Then we're also going to take a look at the singularity function and use those to determine the shear and bending moment diagrams. And last, we're going to take a look at the design of non-prismatic beams to provide constant strength throughout these members. So relating back to our textbook here, we're going to break this module into two different sections, 7.1 and 7.2. The reading guide for Module 7.1 is going to be Chapter 5, Sections 1 and 2. And for Module 7.2, it's going to be Chapter 5, Sections 3 through 5 there. So this is all of Chapter 5 for your reading. I would recommend doing that in advance to going through your lectures. So as I mentioned, we're going to break this module down into two different sections. This first section is Module 7.1. Continuing on with Chapter 5, we're looking at the analysis of design of beams for bending. In particular, for this section 7.1, we're taking a look at our shear and bending moment, taking a look at the diagrams and our relationships with the loads. Now, within this section here, what we're going to do is we're going to obtain the shear and bending moment diagrams by determining our values for our shear and our moment at selected points in the beam. Then we're going to analyze the relationship between the load, the shear, and the bending moment, all three of those right there. So within this, what we're going to do is take a look at some of the key theory, talk about some governing equations, just a few of them, go through some practical applications, and then a lot of problem solving. So the best way to really understand how to draw out these shear and bending moment diagrams is to go through different examples and see how they vary for different types of loads, distributed loads, point loads, different types of beams, things like that. So just going through the problems is a great way to learn this material here. So I would recommend that if you're looking back through your textbook, take a look at similar example problems to what we've done in class, take a look at some of the problems in the back of the book and go through those, and go through all these problems that we go over in class again on your own and see if you can solve them out yourself and draw out those diagrams. So let's start out with a little introduction to this new Chapter 5 and the material there. In particular, let's take a look at the analysis of a simply supported beam. So our goal here is to look at this analysis and the design of the beams. Now, when we're talking about beams, beams are structural members supporting loads at various points along the member. So that's what our definition for beams are. And within this, if we talk about transverse loading to the beams, these are classified as concentrated loads or distributed loads. Now, these applied loads are going to result in internal forces consisting of a shear force from shear stress distribution and also a bending couple, which comes from the normal stress distribution right there. Now, if we're talking about our normal stress, we have a couple governing equations. We can reference back to our textbook, equations 5.1 through 5.3. And normal stress is often going to be critical design criteria right here. So we have, let's take a look here, 5.2 back in our textbook right here. We have our stress right there, normal stress, sigma sub x in our x direction, is equal to a negative right there. Pay attention to your sign convention right there. And this is a my, our moment times y right there, all divided by our I right there, our moment of inertia right there. So then we go back and we can say, okay, if we look at 5.1 for our max load, our max stress right there, our sigma m is equal to the absolute value of our moment times c over I. Recall there is a relationship between our section S right here and our c over I. So this goes back to our equation 5.3 in our textbook. So we can reduce down our relationship here for our sigma sub m for our max stress right there, for our max normal stress there, into an absolute value of our moment divided by S right there. So a thing to note, this requires determination of the location and the magnitude of the maximum bending moment. So now let's take a look at an example here of this analysis of a simply supported beam. So we have a simply supported beam over here in our diagram on the left. So we can see we have this beam ACB. So there's our beam, there's point A right there, there's point B, there's our two supports right there. So this is a simply supported beam right there, A and B. You see we have this section that we're looking at C right here. And now we can see this has a distributed load W, so there's our distributed load W right there, and two external loads, P1 and P2. So there's our P1 and there's our P2 right there. So this is our transversely loaded beam, which is a simply supported beam at points A and B. So the next thing we want to do in our procedure for analysis for a problem like this, if we have this simply supported beam, what we want to do next is take a look at this given information, this diagram here, and from that create a free body diagram. So that's what we're doing in part B of this diagram over here of our figure. As we can see down here, we have a free body diagram, and what we want to do within this diagram here is for our simply supported beam right here for supports at A and B right there, what we want to do is we want to replace those by reactionary forces. So we have R at A and R at B right there. So there's our RA, there's our RB right there on this figure right there. So now we've taken that information from our simply supported beam up here from our problem statement or wherever it might be right there, and we've gone ahead and now created a free body diagram. So now we can see all these forces, these loads acting on it there. Now, with this problem here, where this differs a little bit from what we've seen maybe in our statics course before when we've looked at problems like this, is now we're also interested in these internal loads. We're not just looking at our external loads and doing our equilibrium equations for that. We're interested at a certain point in the beam, what's going on? What are our stresses? What's our strains? What's internal to the beam that's happening there? So that's when we go to this section C right here. So at C, we want to actually cut this. So that's what we see down here in part C of this diagram, where we have a cut at that section C, and it shows our internal loads. Well, what are our internal loads at that section C? Well, what we have here is we have our V, our shear, and our M, our moment right there. So there's our distributed load right there, there's our reactionary load right there, and there's our external load P1 right there, this point load right there, and then we cut it at C. So we go back up to the part there, we're cutting it right there at C like that. We can see at C, now we have, there's our shear, and there's our moment right there. So this is a free body diagram to find our internal forces at C. I know this is often a question. I've had a lot of students ask us, well, how many free body diagrams should I draw? Can I do it all in one? I wouldn't suggest doing it all in one. I really like what we've done here. We've kind of taken the entire figure and drawn out an overall free body diagram that we can use as a reference. And like I said, if this was just statics, this was great. We could do our equilibrium equations, solve for the unknown, wherever it might be, and done. But then, if we're sectioning it, we want to break it down and do a free body diagram for each. So we can do a free body diagram from A to C, and then we could also do one over here if there was interest over here of CB, and do the other side of that for another free body diagram. So having multiple free body diagrams is allowed, and it is a good idea, and it really helps simplify things down, especially even with this one here, only a couple loads, but over that small section, that can get confusing quickly. To have it nice, drawn out nice and big so you can see exactly what's going on is very helpful as you're going through and solving the problem. So as we continue on with our introduction to Chapter 5 in our textbook in Module 7, what we're going to take a look at next is the classification of beam supports. So this module, Module 7 here, is devoted to the analysis and design of beams under transverse loadings consisting of concentrated or distributed loads. So the beams are classified according to the way they are supported. So this is going to be important to understand how they're supported. And when it's something that's worded in a problem statement, they say, okay, it's a simply supported beam. What does that mean? It's an overhanging beam. It's a cantilever beam. All these different things. We really want to be able to clearly understand when it says that, we know exactly what to draw out. Because as we've seen, not every single problem we're working with, whether it's a realistic problem at your job, a design project, or if it's a textbook problem or an example problem in your textbook, they don't always give you the figure showing it what it is. They might just say it's going to be a simply supported beam. You need to understand what that is. They might give you the dimensions in the word problem, but you'll be responsible for drawing out the diagram for what that actually is. So this is right here is very important, as we can see in this diagram below. Now within this right here, only statistically determinate beams were considered. This is where all the support reactions can be determined by statics there. So going back to your statics class, these should all look relatively familiar. So let's just take a look at the top where we're talking about these statically determinate beams right there. So if we're talking about statically determinate beams right there, this is going to be A, simply supported beam. And you can see right here, okay, there's my support there, support there. This is similar to the example problem we just went through there. And you have a distance, so the length of the beam from support to support of an L right there. Then we have in part B right here for our statically determinate beams an overhanging beam. So we can see in our overhanging beam right here, again, now you have those two supports similar to what we saw in a simply supported beam, but rather than the beam length ending with this support right here, it now overhangs, so hence the term overhanging beam. And then we have a cantilever beam, and you've seen this before, and you will continue to see it in some of the labs and other classes that you go into. So you just have the one fixed support over here, and then you have the total length of the beam, your L right there. But now if we move on to statically indeterminate beams right here, we have a couple different examples. So examples of statically determinate beams that we saw before include the simply supported and two fixed at one end, whereas statically indeterminate examples show a beam simply supported at 3 points right there, fixed at one end and simply supported at the other end, or fixed at both ends right there. So that's why it's statically indeterminate, because we aren't necessarily able to determine all these support reactions right there with just our statics. So let's take a look at these examples here. So in the first example of a statically indeterminate beam right here, we have a continuous beam. So the continuous beam, this is the case down here, we have 3 points. It's simply supported at 3 points right there, which makes this a statically indeterminate example down right here, and this is what we're calling a continuous beam. Then we go on to part E right over here. So this looks similar to our cantilever beam right here, but now there's also a simply supported end as well. So you got a fixed end and a simply supported end right there, and this is a little beam like that. So this is a beam fixed at one end and simply supported at the other. And then last case over here, it's fixed at both ends as we talked about down there. So this right here is a fixed beam right there that's statically indeterminate because it's fixed at both ends right there. So now let's take a look at shear and bending moment diagrams. The first step within this here is to identify what our shear and bending moments are. So let's just take a look at this example again where we have a beam with multiple loads. This is used to show that wherever this cut is made, in this case here, it's being made at point C right here. There's our cut for our section at C right there. Wherever this is made, the internal shear and moment will have opposite directions, and this is going to depend upon which side of the cut is kept. So on either side of that cut is going to have these opposite directions. So now, another thing to note here is that deformation of the maximum normal and shearing stresses is going to require identification of maximum internal shear force and our bending couple. So we'll need to identify those. So now our shear force and our bending couple right there at a point are determined by passing a section through the beam and applying our equilibrium analysis on the beam portions on either side of that section. So that's going to be kind of our procedure right there in order to determine those. So let's take a look at our diagram up here on the top left right here. Within this diagram right here, what we're doing is we're trying to determine our shear force, our V, and our bending moment, M, at a given section. Now this section could be anywhere along the way, and our diagram here at A, we've determined it to be at this point C of interest right here. So we can see we have a simply supported beam again. We have our simple supports here at A and at B, just similar to the other example problem we looked at. Now we've also got 3 loads here. We've got our distributed load W, we've got our external point load P1, and an external point load P2. So this is a loaded beam with a section indicated at an arbitrary point over here, in this case here at C. So from this here, what we want to do, similar to what we did in the previous example, is we want to go ahead and determine and draw our free body diagrams based upon the information given with this. And from our free body diagrams, this is where we're going to be able to determine our shear force and our bending moment using our equilibrium equations. So we take and draw out our free body diagrams. So remember, the first thing we want to do in that procedure for analysis with a simply supported beam right here is replace these supports with our reactionary forces. So that's what we do here. So this case here, I did out both sides. In our previous example that we went through, we only did the left side up to C. Now we're going to do both sides of that there, and then from that, we can talk about where we have these moments at opposite directions depending on which side of the cut is kept. So that's what we'll do down here in part B. Here's our free body diagrams of the left and the right sections at this point C right here. So this is great. You can see I like the fact that I drew this directly below our diagram up there because I can drop this right down, so I make sure that this is that same distance X. It looks proportionate as we're doing this out here. So there now, instead of our support right there, here's our reactionary force, R at A right there, and that's our supported end right there at A. Then we have our external load P1, our distributed load W, and then at our cut right here, at our section right here, now what we have, there's our shear force right there, there's our V, and here's our bending moment M right there. So that's the left side of our beam right there. Now we're going to take a look at the right side of our section right here. So now we go from this C right here over to B right there for the right side of the section at C. And what we see now when we draw another free body diagram of that over here is we have this right here. So this one now, what we can do, we'll say, well, we want to replace this simple support right here by a reactionary force, our R sub B right there. Then we have our external load. There's our P2 right there. And then now we can find our V prime and our M prime right there. And now we can see that these are opposite directions to what we saw when we looked at the left side. So the left side and the right side do have these opposite directions as we would expect to see. Now something to think about here is for this problem, it's not super complicated, but there is a lot going on. And maybe it's a good idea to draw that intermediate free body diagram of the beam as a whole, where we replace these two by reactionary force A and B, and then you can take a look at that as a whole to break it down to your left and right of that section at C. So you could draw in another one just for your own benefit right there to help see what's going on, and maybe we did something differently later on with this distributed load W, things like that. So maybe it would be a good idea to draw an intermediate free body diagram for certain problems. You don't have to, but sometimes it'll help you keep track of things as you get into these individual left and right sides at different sections, and maybe we're trying a section when x is equal to 1, x is equal to 2, x is equal to 5 at different lengths along the beam, sectioning it there to see how things change along it. So for each one of those, you'd have different free body diagrams for that. There are at least different positions of things. If you cut it a little bit too short, maybe you'd only look at the section here. All of a sudden, that free body diagram is different because you don't have the P1 or your W. Or maybe you draw it here where you just have the P1 in the end, but you don't have any distributed load W on it. Things like that. So pay attention to where your sections are and what that means for your free body diagrams. The next thing I want to touch on when we're discussing our shear and bending moment diagrams right here is our sign convention for shear and bending moment itself. So that's something that's important right here. So let's take a look at these three different examples in this bottom diagram down here. So at part A, we have these internal forces right there. So we did that sectioning at wherever it may be. Let's just say we did it at C like that there. So then you got your shear force V and your V prime that are opposite directions. And then you have your M and your M prime, again, going opposite directions right there. So this is a positive shear and a positive bending moment right there. So then we can move on now to part B right here. We can take a look at the effect of external forces, or a positive shear right there. And then we can see over here at C, we have the effect of external forces as a positive bending moment right there. So we've broken it down right here between our shear, positive shear, and our positive bending moments right there. So we can take a look and see which way is it bending up, which way the shear is going, which way is it clockwise, is it counterclockwise. So keeping track of that sign convention on how you've determined what to be positive, whether it's clockwise, counterclockwise, your right-hand rule as you're setting everything up. Pay attention to the sign convention. And again, going back to this here, that there's going to be opposite directions depending on which side of the cut you're on right there. So are you looking at an individual free body diagram here, and what is the sign convention of the moment and shear in this versus what is it in here? We're looking at something as a whole over here. We're looking at a positive shear or a positive bending moment on a section as a whole. So those are things to consider, but pay attention to your sign convention, pay attention to your right-hand rule, pay attention to your given or chosen coordinate system in this, and always make sure to double check your sign convention, even with your equations. You might have a negative moment, but there's a negative sign in your equation for your stress, things like that. So pay attention to sign convention and write things out. So now let's take a look at an example problem here. So we're going to take a look at sample problem 5.1. So in this problem right here, we can see we have a timber beam. So for this timber beam, we have the shown loading above in this diagram right here. Now what they want us to do from this information in the diagram that we see there is to draw our shear and bending moment diagrams, and also to determine the maximum normal stress due to bending. So we got a couple different things. We have two diagrams. We have to draw our shear diagram, and we have to draw our bending moment diagram. And we also need to do the calculation in order to determine what that maximum normal stress is due to bending right there. So we can see we have the situation right here. We have the two supports right here on the bottom at D, and we have one at B as well right there. Then we can see at point C, we have this external load of 40 kilonewtons, and at A, we have an external load of 20 kilonewtons right there. We can also see we have the distances from the end, so whether we're going from A or we're going from D here, that's up to us. We can determine which one we want to do for our calculations, for our equilibrium equations. We can see we're 2 meters away when we get to C, then between B and C is 3 meters, and then between B and A is 2.5 meters right there. So again, think about this. We're going to want to pick a datum at the end, a zero reference, and go from there. So if we did pick D, we'd say, okay, C is 2 meters away. Okay, B is 5 meters away as we add those two together. We say, okay, A, this is 7.5 meters away by the time we get over here to our external load of 20 kilonewtons. So as we think about this here, the first thing we'd want to do is create our setup page. If we're doing this out by hand, we create that setup page. What is all of our given information? Let's label what these loads are. Let's again cover the 4 things for each of those variables: the variable name, the numeric value, the units that we're using. We're going to also want to relate it back to how it relates to our problem itself. So all 4 of those things are going to be included in our setup page. As we do that, then we can look at that setup page and say, okay, there's all my given information. Here's everything they asked me to solve for in this. Now let's go ahead and establish a procedure for analysis. So that's what we'll do right here as we take a look under the solution section over here, is come up with a general procedure for analysis for how we would solve this problem out. So we're treating the entire beam as a rigid body right there. So we can also see this is a timber beam right here, and we have the dimensional lumber right there, 80 millimeters by 250 millimeters right there. We're treating this as a rigid body and determine our reaction forces. So our reaction forces, as we recall from earlier in this module here, are going to be at points D and B right there. So we want to get our reactionary forces for that, and remember the next step after that is do our free body diagram once we've created those reactionary forces right there. So then what we also want to do is we want to section the beam at points near supports and load application points right there. Then from there, we apply our equilibrium analysis on the resulting free body, so there's where we do our free body diagrams, in order to determine those internal shear forces and our bending couples as well. Next, we want to identify the maximum shear and bending moments from plots of the distributions. So that's is where we actually draw our shear and moment diagrams right there, and what we're using them for. We're using them to determine the maximum shear and bending moments for these distributions. Last, what we're going to do is apply our elastic flexure formulas in order to determine the corresponding maximum normal stress, because recall, if we go back again to our problem statement here, our maximum normal stress is the last thing they want us to solve for. So it's great that we have our problem statement, our diagram here, and our procedure for analysis, and that's really going to help us. But now we can see, even as we get down here, like, oh yeah, I have to do this last part of this. So that's why I really do stress the importance of creating a setup page when you solve these out by hand, because you can quickly flip back and label it out A, B, and C. A, I'm solving for my shear diagram. B, I'm solving for my bending moment diagram. And C, I need to find that maximum normal stress due to bending right there. So I have those all clearly laid out on my setup page. So as I'm going through and working through my solution, I don't get to a spot where I think, yeah, I'm done with this problem. I go back, oh wait, no, I also had to solve for my part C here to find that maximum normal stress right there. So being able to flip back to that, not only to reference all your given information, but also to reference what they'd ask you to solve for in the problem is very helpful. Now that if we were doing this problem out by hand, we have that setup page created. We now have this great procedure for analysis that we can step through as we begin our solution. So remember the part of the procedure for analysis that told us to section the beam at points near supports and load application points, and then apply our equilibrium analysis on the resulting free body diagrams to determine the internal shear and bending couples. So that's what we're going to do right here. As you can see over here in this figure 1 right here, we have 6 sections identified for analysis right here in the free body diagrams for each section. So we can see, okay, we've done it right here. Again, this is points near supports and load applications. So we section it right there, near that right there. So you can see our dotted line right here. So we call that 1. Then we have our second one right here, right near this load application there on both sides of that load application for 2 and 3. Then we have it on both sides of the load application for 4 and 5 right there at point C. And we have it right near here at the end right here at point D, near that support right there. So we got it by the supports for 1 and 6, and by either side of the load applications for 2, 3, 4, and 5. So that's what we're seeing over here on the left side in our diagram. So our first step in our procedure analysis actually told us to treat the entire beam as a rigid body right there. So that was our first step in our procedure for analysis right there within our solution. And from that, we can determine our reactionary forces right there. So that's why we can see in our diagram over here on the left, we already have these values here. And that's because we've gone through, done out our free body diagram as a whole. And from that there, we were able to determine our reactionary forces. So what we can do is we can say, okay, the summation of forces in our y direction is equal to 0. So that's our equilibrium equation that we can use right there for our forces. Nothing acting in our x direction right now, so we're just dealing with our y direction. And this is also saying that the summation of moments about B right here are going to be equal to 0 as well. So from that right there, we can do our equilibrium equations, and we can say that, well, from this right here, our reactionary forces at B and D, whereas the 2 supports are right there, are going to be equal to 46 kilonewtons and to 14 kilonewtons. Now let's go through how we came up with those values for our reactionary forces. So we wanted to go back to that procedure for analysis again, where we're talking about treating the entire beam as a rigid force and determining these reactionary forces. Well, in this step here, we start with our initial diagram that we have up top here. So again, we can see our simple supports at D and at B, and that's what we want to determine these reactionary forces for there. And we can see we have our external loads of 20 kilonewtons and 40 kilonewtons acting at A and C respectively there. And we have our distances between all of these there. So what we want to do next is from that initial diagram, create our overall free body diagram for the entire beam as a rigid body right there. So that's what we do now. We create this free body diagram right here. So I replace these 2 simple supports here at D and B with these reactionary forces for R sub B for the reactionary force at B and R sub D for the reactionary force at D. And then from there, what I want to do is come up with my coordinate system. So I'm choosing a standard XY coordinate system where X is positive to the right and Y is positive up right there. And that's going to be important as I do out my equilibrium equations. So I want to do two different equilibrium equations out right here. I want to do a summation of forces in my Y direction. There's nothing acting in my X direction. And then when I do that out, I determine that there's two unknowns in one equation. So I need a second equation. So my second equation is summation of moments. And now I have a decision. What do I want to sum my moments about? I can do it about D. I could do it about C, I could do it about B, I could do it about A. Well, I want to eliminate one of the unknowns, and one of my unknowns is going to be these reactionary forces there, so I'm choosing to sum my moments about my point B right here. So let's start out with our summation of forces. We have our free body diagram. There's our external load of 20 kilonewtons there. There's our external load of 40 kilonewtons there. And I can reference up top there to get my distances and where those are located. Then I have my R sub D for my support reactionary force right there. My R sub B reactionary force right there for supported B right there. So now looking at that, I can say, okay, the summation of my forces for my equilibrium equation, summation of my force in my Y direction is equal to 0. What are my forces in my Y direction? So that's where that free body diagram is so helpful right there. I can say, oh, there's all my forces in my Y direction. So I have a 20 kilonewtons, 40 kilonewtons, RB and RD, where my 20 and 40, according to my chosen coordinate system here, are going to be negative. So this is where that sign convention we talked about becomes extremely important right there. So these are negative for me here, whereas my R sub B and my R sub D, my reactionary forces, are positive for my chosen coordinate system. Now I very easily could have flipped that over and said Y was positive down and negative up and flip those signs, and that's fine, but I have to, one, pay attention to my sign convention for that, and then also when I'm doing out my moments, my right-hand rule, pay attention to that as well. So with this right here, if I take this and I take my right hand rule, I can see I'm positive coming out like this here as I curl my fingers toward my Y, towards my X. So I want to make sure when I do my moments, I'm correct on that. So I'm saying that counterclockwise is positive and clockwise is negative for that there. So that'll be important when we get to moments. Well, now we're back to forces. So what are my forces? I go back to the free body diagram. Well, I have a positive R sub B and a positive R sub D. So I say RB plus RD for the summation of my forces minus 20 kilonewtons minus 40 kilonewtons is all equal to 0 there. Now I can sum my moments about B right here. So summation of moments about B right here, there's my point B right there, is equal to 0. So what are my moments about B? Well, I can use that free body diagram, and I can use the distances from my initial diagram up there to figure out it's force times the perpendicular distance away from that point we're summing the moments about. So I can say, right, well, if I'm dealing with this right here, I have 20 kilonewtons times this 2.5 meters. So 20 kilonewtons times 2.5 meters. Now do out that right-hand rule. Curl this, boom, okay, that's going counterclockwise. Around that point there, that's positive. So there's a positive moment there, 20 kilonewtons times 2.5 meters. Minus now, I have this right here, my 40 kilonewtons times my 3 meters distance. Now this is negative, so it's going clockwise, so that's the negative it chose according to my chosen coordinate system right here. So this is a negative 40 kilonewtons times 3 meters. And then I have, last, I have my reactionary force at D times this distance right here of 2 plus 3 meters, which is 5 meters totals right there. So 5 times R sub D. And I do my right-hand rule out. That's going counterclockwise. That's positive for me. So I have this now as positive 5 meters times my R sub D is equal to 0. So from this here, I take a look now, I've got these two equations right here, and I can see that I still have two equations and two unknowns. Now that I have my two equations and my two unknowns, I don't know my R sub B and my R sub D, so those are my two unknowns right there. I can now take my equilibrium equations right here, my summation of forces in the Y direction, and my summation of moments about B right there. So I can take a look at these and I can say, okay, well, within my summation of moments about B, I only have one unknown and one equation. Whereas my summation of force about Y, I have these two unknowns in one equation right there. So we can solve our summation of moments about B directly to get our value now here for our R sub D, our reactionary force at point D. So that's exactly what we do. We're going to solve our moment equation for our R sub D. So with that there, we can now come back up here and say, okay, well, this right here is our 20 kilonewtons times 2.5 meters minus my 40 kilonewtons times 3 meters plus my R sub D times 5 meters is equal to 0 right there. So I have this information here. The next thing I want to do is simplify and reduce this down. Well, I can say let's just multiply through. My 20 times my 2.5 gives me 50 in units of kilonewtons times meters. And then I have my 40 times my 3 is 120 kilonewton meters, but this is a negative value right here. So again, pay attention to your sign convention with this right here. This is our negative value right there. And this is plus our 5 times our R sub D right there, which will still have the same units of kilonewton meters when we plug in our value for that or solve for our value for our R sub D, which would give our R sub D a value of units of kilonewtons right there. So let's combine this a little bit now. We can say 50 kilonewton meters minus 120 kilonewton meters is negative 70 kilonewton meters right there, plus our 5RD is equal to 0 right there. We can rearrange this. Let's add our 70 kilonewtons to both sides. So we can get rid of that negative, add this over here to our right side of the equation. So we end up with 5RD is equal to 70 kilonewton meters right there. Now what we can do is we can come down here to this equation now, and we can say that R sub D is equal to 70 kilonewton meters divided by 5 meters, and we can see our meters cancel right there, which leaves us with just our R sub D is equal to 14 kilonewtons. So now we have a value for our R sub D. So now that we've solved our summation of moments equation right here for our value for R sub D, we can take this R sub D value right here and plug it back into our force equation up top and solve for our R sub B. So that's what we do now. We take this R sub D, we come back up here, we plug it into our summation of force equation, which was two unknowns in one equation. Now it'll be one equation, one unknown, and we can solve for our R sub B. So that's what we do there. We take this R sub D is equal to 14 kilonewtons, plug this value for R sub D right back into this equation right here. So we plug that in and we say, okay, now R sub D is now our 14 kilonewtons right there. So this right here, we can move down and solve for our R sub B. And we solve this for R sub B, we say, okay, our R sub B plus our 14 kilonewtons minus 20 kilonewtons minus 40 kilonewtons is equal to 0 from our above equation there. And then we say, well, let's combine our negative 20 and our negative 40 kilonewtons right there. It becomes a negative 60 kilonewtons right there. So we have R sub B plus our 14 kilonewtons minus our 60 kilonewtons is equal to 0. Or we can rearrange that, put our 60 over back onto the other side over here, and we can say now, well, this is equal to a positive 60 kilonewtons over on the right-hand side over here. So R sub B plus 14 kilonewtons is equal to 60 kilonewtons. We can subtract 14 kilonewtons from both sides, and what we find out then is our R sub B is equal to 46 kilonewtons. So now that we've completed that there, we can see where these values for our R sub B and our R sub D came from there by doing out that free body diagram for the entire beam as a rigid body in order to determine those reactionary forces. Our reactionary force at B was 46 kilonewtons, and our reactionary force at D was 14 kilonewtons. Now, from here, what we want to do is do that same process again, but for each of these 6 different sections. So if we recall over here in our diagram, we broke this down into 6 sections identified for analysis for the free body diagram, where we broke these off right near the reactionary forces and right before and after our external loads. So that's what we want to do now is go through each one of these free body diagrams individually, do out these equilibrium analysis for each of these ones here, and solve for our V's and our M's, our shear forces and our moments. So that's what we're going to do now. Let's just take a look at the first one. We had our section 1 right here. So we're going to section this right there like that. And what we're going to do is now we're going to go through and take a look at this free body diagram. So this is our free body diagram when we do that section right there. So we can still see we have this external load of 20 kilonewtons right there. And when we do our section right there, we have our shear force and our moment right there. Now pay attention to the directions. Our shear force is going down, as is our external load right here of 20 kilonewtons. Those are both negative. So according to our chosen coordinate system, where y is positive up, these values are both going to be negative. But our moment right here, if we do out our right-hand rule, that's going counterclockwise, that's going to be a positive value there. Now what we can do is take a look at our second section right here. So again, if we were to go through this by hand and solve this out, I would highly suggest looking at each one of these on a separate page right here, drawing out your free body diagram on its own, doing out your equilibrium analysis on its own right there, so it doesn't get quite as congested and convoluted as we're seeing here. But for this example, what I've decided to do is leave it all here just so you can see how each of these line up with our overall free body diagram from the top up here, and we can see our distances and everything like that. So this is just for this sample problem, so it's all on one page for you. If I was solving this out by hand, I would do these each on a separate page for each of these 6 different sections. So now we'll move on to this section 2 right here. So we can see this section is right before our support, our reactionary support at B right there. So our only external load is still this 20 kilonewtons right there. So now we can go through and say, what are the summation of our forces? Well, our forces acting on this, we have this 20 kilonewton force acting right there. So there's our negative 20 because it's going on a negative y direction from our chosen coordinate system. And we have this shear force right there of negative V. Move our V to the other side, we see that negative 20 kilonewtons is equal to V2, or V2 is equal to negative 20 kilonewtons. So now we have a value for that shear force there. So now we can do our moments. Well, if we take our moments about our point 2 right here, well, we can now say we have a force times our perpendicular distance. So we have 20 kilonewtons times 2.5 meters plus our moment right there at M2 right there. So at R2 right there. So we can see, well, this is actually going counterclockwise, so that's positive. That's going counterclockwise, so that's positive right there. So we have 20 times 2.5 right there. So we have our 50 kilonewton meters right there is equal to a negative M2, or M2 is equal to negative 50 kilonewton meters right there when we solve for that. Now we want to continue on and do the same thing for the rest of these. So if we're at section 3, at section 4, at section 5, and at section 6, we're doing the same thing out. We come up with our free body diagram. We look over here, create from our free body diagram our summation of forces, our summation of moments, do out our equilibrium analysis right there. And what we can see when we do this out now is we can say, okay, well, if we get down to 3 right here, well, now we've got this reactionary force at B coming in here, so we got more stuff to consider when we do out our summation of forces and our summation of moments. And then when we get down to here to section 4, we can say, well, we've got that reactionary force, we've got the external force here, now we got a longer distance before we get to our V4 and our M4 there. Then we get to section 5, well, now we've also got this external load at C coming in here, 40 kilonewtons. And then when we get to the over at 6 right here, we now have our external loads right there and our reactionary force and a little bit further there. So all of that comes into play, and this is where we get these values right here for V3, 4, 5, and 6, and M3, 4, 5, and 6 by doing the same process that we did here for our summation of forces and moments, our equilibrium analysis, which we can reference back to how we solved it for reactionary forces, how I would do it by hand every time, where I actually draw out the free body diagram for each of these separately, do out my summation of forces, my summation of moments, solve each of these step by step for each of those variables in order to get these values that we now see and get down here. So this is a really condensed version going very quickly through this for 3, 4, 5, and 6. And again, I would highly suggest doing this out by hand and not trying to crowd it all into one page like we see here. So now what I want to do is take that information that we gathered, all that information for individual values for our shear and our moments, and use that to create our shear and moment diagram. So I copy over everything, I have it highlighted down here, boxed in green right here, for all those values for each of those corresponding 1, 2, 3, 4, 5, and 6 sections we did there. So we have our shear forces and we have our moments corresponding with each one of those. I redraw my diagram up top here, and then what I want to do is drop lines straight down. So right there where our 20 kilonewton load is, I draw a line straight down. That for our shear and for our moment right there. Where our reactionary force is right here at B, I do the same thing. Same for external force here at C, I draw the line straight down there. And then for a D as well, I draw that line straight down there. And that's what I'm going to use to draw out my shear and moment diagrams. Those lines right there are going to help me. Now with that, what I also want to do is identify my maximum shear and bending moments from the plots of the distributions right there. So take that information right there. Well, we find if I go down to all my values there, my max shear is 26 kilonewtons, that's right there. And my max moment right here is the absolute value of my moment at B right there, which is going to be my 50 kilonewton meters right there. So I take that information, I can come over here and I draw those in. Now I can see where those values come from right there, plug those in, and I draw my line straight down. So let's take a look at my shear diagram first. So my shear diagram, I come down here and I say, okay, at the beginning here, what is my value? What is my shear, my V1? Well, that's negative 20. So I draw that in there. There's my negative 20 right there. What is at V2 right there, this line right here? Well, that's going to be a negative 20 as well. I draw that line in there. So I have a straight line across both of those there. Then I come over here. Well, at 3, what is my value? Well, this is my 26 kilonewtons, which is my max right there. So I draw that in right there. And then what is at 4 right here? I come down. Well, my 4 right here is at 26 kilonewtons as well. I draw a straight line between those two as well. So now I can see, okay, my shear as I go from A to B is going to stay at this value right here of negative 20 kilonewtons, and as I go from B to C right here, that's at this value of 26 kilonewtons right there. So then I move on, I want to go from C to D. Well, I can say, well, at 5 right here I have a negative 14, and at 6 right here I have a negative 14 as well, so I draw a straight line right there. So that's why I have a straight line at negative 14 as I go from C to D right there, and that's how I come up with my shear diagram. Now I do the same thing for my moment diagram. Again, I like to line everything right up right there. So at the beginning, my M1 right here is 0. So there's my 0 value right there. My M2, there's my 50 kilonewtons right there and 50 kilonewtons right there, which is also my max right there. And then I have over here, when I come back up here between my B and C, I can see when I get back up to C right here, well, I have these values of 28 kilonewtons right there, 28 kilonewtons there, and then I go back down to 0 at the end here. So now I can draw a line between all of these points like that there to draw out my bending moment diagram like this right here. So now I have my shear and my bending moment diagrams that correspond and line up with my initial diagram up here, my free body diagram from up here above, at each of those points, A, B, C, and D, and I use all 6 of these sections to get the values to draw in those lines that go from A, B, C, and D within that there. Now that we've completed these shear and bending moment diagrams, we need to go back to our setup page, back to our original problem statement, figure out, is this everything they asked us to solve for? And no, it's not. We need to find the max normal stress as well. So that's what we're going to pick up right here. We're going to apply our elastic flexure formulas in order to determine the corresponding maximum normal stress right there. So we can reference back to these equations we talked about at the beginning of this module here, where we have equations 5.1 through 5.3 in our textbook right there, where this right here, our 5.1, is giving us this value right here for our maximum normal stress right there. So we can see from that there, we can then calculate our S value right here, which our S value is going to involve our C and our I, a moment of inertia right there. So we want to be able to plug that in. So we do that for this shape of our beam right here. And we can say, well, we have that information given to us for that beam shape right there. So we can calculate out our value right here for our S from based upon that right there. So S is going to be equal to 1/6, our base times our height of that piece of lumber right there, where they gave us that information right there. And the height is squared. So this is 1/6 times the base of it is 0.08 meters. Make sure we go to meters, not millimeters. And our height of this is 0.25 meters right there, quantity squared. So we do that out, and now we can get our S value here of 833.33 times 10 to the negative 6 meters cubed right there. So that means now we can go back up to this equation 5.3 in our textbook, plug in this value right here for our S value right there, and our maximum normal stress is equal to absolute value of that maximum bending moment, which we just found to be 50 kilonewtons from all those free body diagrams and equilibrium analysis equations there. Plug that in. 50 times 10 to the third Newton meters divided by 833.33 times 10 to the negative 6 meters cubed right there. Well, what we end up with there is units of pascals when we do our unit analysis, and our sigma sub m is equal to 60 times 10 to the 6 pascals. So this is the final thing that asked us to solve for, was that max normal stress right there for this problem, and that's how we do it, relating back to those equations 5.1 through 5.3 in our textbook. Now let's continue on with the section here. We're going to discuss the relations among load, shear, and our bending moment right here. So we have as an example off here on the left in our diagram here, where we have this beam ACBD. Well, this is a simply supported beam, so you can see our simple support right here at B and A right there. Those are two supports right there. And loaded, now the difference now is here, this is going to be loaded with a variable distributed load W right here. So you can see the shape of this distributed load right there. So it's a variable distributed load W. Now the other difference is here is we're going to take a look at a cutout. So rather than just a section line right there, we're going to take a cutout from C to C prime, and that's going to be shown to have a dimension to it. And this dimension is going to be delta x long. And we're going to look at that as its own free body diagram. So rather than before we took a section, just look at part of something or half of something up until that section line, now what we're going to do is we're going to actually pull a full section out of it that has this dimension of delta x right here. And that's what we see down here in our diagram below in part B right here. This is the free body diagram of that element right here that we're taking out of this beam right here, this ACBD simply supported beam right there. So we bring that down there, and now we can see what's going on. Well, we've got right here, we've got this W times our delta x right there. We've got this distance right here, which is half a delta x, which is the center. So we're looking at the center of the element right here. So if the whole width of the element is delta x, this is the half of delta x right here, where we have that load right here in our dotted line, our W delta x right there. And then we have over here, we can see our shear on either side. And we have over here on the left side, here is our shear force and our moment. But on the right side at C prime over here, you can see what we have now is V plus V prime and M plus, I'm sorry, V plus delta V, and then we have an M plus delta M. So you have that change in shear, that change in moment right there added to the moment that we see right there, which is the V and M that we see on the left side over here at C. So now let's first take a look at this relationship between our load and our shear right here. Now in order to do this, we're going to use this free body diagram that we see down here in part B of this figure on the left right here, where this is the free body diagram of that section that we pull out from C to C prime right there. And first, if we're talking about between the load and shear, let's just take a look at summation of our forces in our y direction right now there. So if we look at this right here, okay, the summation of forces in our y direction equal to 0 from our equilibrium analysis right there. Well, we come down here and say, what are our forces acting in our y direction right here? Well, what we have right here is we have this v right here. So there's our positive v going up like that, minus, you see going down in our negative y direction, we have this v plus delta v right there. and then we also have a minus our W delta X right there, which this comes from that distributed load W up top here, acting at the center of our element right there. So from that there, what we want to do is we want to solve for this delta V right there. So this delta V, we can rearrange this stuff and move it around a little bit, and what we find out then, when we solve for this here, is we have the V minus V right there, those end up canceling out, shift things around the other side of the equation, and we end up with delta V is equal to negative W delta X. Well, if we want to find out what that negative W is right there, we can say, well, delta V over delta X is the same as dV dx right there is equal to our negative W right there. So then we can rearrange this a little bit more and say, okay, our change in our shear from C to D right here, which is the area under the curve between C and D, all the way to right there, is going to be equal to. So now just pass not just that C to C prime, but if we want to go from C to D right there, so the change in the shear from C to D is equal to the integral from X at C to X at D. So there's our X value at C right there, and then if we were to come up here like this would be our X value at D right there. So that's how we can utilize that information we get from our free body diagram from that element right there to now bring this into any point right there, any section in the thing right there. So we want to find the area under the curve between C and D. That's the area under the curve we call as an integral. So if we go from C to D right there, we go from right here to right here to find the area under the curve. So that's why our limits of integration go from X is equal to C, X is equal to D right there, whatever those X values are right there, times our W X right there. So this right here, W dx right there. So this is where our dV comes in, this is the dV right there, the change in the shears right there. So this could have been from A to D, could from A to C, but we were just going from C to D for our case right here. So that's where that dV dx comes in. We rearrange this right here, take the integral right over there. So the dV is the difference in those shear forces right there to get this relationship. Now that we have the opportunity to go through and look at this relationship between our load and our shear, come up with this general governing equation down here with the integral right there, which represents the area under the load curve between C and D. So between our C and D right there, because that's where we took this element out, was from C to C prime, was in between C and D right there. Now what we can do next is we want to take a look at the relationship between our shear and our bending moment. So now we can come back down to this free body diagram over here on the left, and we can say, okay, using our equilibrium analysis, let's take a look at the summation of moments about our C prime right there, and this is equal to 0. Now, what are the moments acting about C prime? Well, at C prime, we have this m plus delta m, and this is positive because it's going counterclockwise. And then we have this negative m over here, so this m right here, and that is going to be negative because it's going clockwise. And then we have the moment from this force times this perpendicular distance here, which is, again, is going clockwise, so that's a negative v times delta x, force times perpendicular distance right there. And last, what we have now is we have this force right here from our distributed load, our w delta x there, times, we can see this is right at the center of this here, so this is a 1/2 x for the distance right there. So this is going to be plus, because now this is going counterclockwise, of w delta x was our force times that distance, which is delta x over 2. This is all equal to 0. Now from this here, what we can then do is rearrange, simplify this down, see what cancels out within this here, and what we end up with is we have a delta m is equal to our shear force V times delta x minus 1/2 w times delta x squared there. So we can go through, rearrange, and simplify this down a little bit more, and what we find out when we do this here is that we can pull out a delta x, we can rearrange, cancel some things, and we left with a delta m over delta x is equal to v, or dm over dx is equal to v. So our shear force is equal to the change in that moment with respect to our distance right there. So again, a dm is our change in our moments right there. So we have a moment at C and a moment at D right there. So we can say md minus mc is our dm right there, which is equal to the integral from C to D, again right there for our limits of integration right there, times v dx from this equation right there. So now we have an integral again now for this right here, and this is the area under the shear curve between our C and our D. So again, pay attention, the top one is the area under the load curve, and this one is the area under the shear curve between that right there. So those are our two governing equations that show us the relationship between load and shear with this relationship here, and between our shear and bending moment with this equation right here.